I want to welcome all of you uh, back to VLSI Symposium and Industry Forum. This is our second session of Industry Forum, and we have a great lineup of three speakers for this session today. Our first speaker will be from Imagination Technologies, followed by Synopsys, and finally Texas Instruments. So let me introduce my first speaker here. Our first speaker is Shreyas Derashri from Imagination Technologies UK. Shreyas is currently VP of Compute at Imagination Technologies. He is responsible for Imagination CPU, AI, and heterogeneous compute platform and product end-to-end solutions. He has 20 years in tech industry. He has got MBA from Cambridge Judge Business School and Masters in Analog and Digital IC Design from Imperial College London. He has double gold medal for his bachelor's degree. So without further delay, I'd like to ask Shreyas to come online and share his presentation and share his thoughts on his talk today with title New Era of Compute. So Shreyas, over to you.
Great. So I will start. Thank you, everyone. Good afternoon for people who are joining from in India. I'm joining from the UK, so it's early morning for us. So I'll be talking about the new era of compute and how we see compute evolving in the industry over the next decade or so. So we probably all heard of laws of physics, laws of thermodynamics. In the similar way, there are certain laws that have guided us around the compute performance for the last sort of four or five decades. Pretty well known amongst them is Moore's law. Moore's law is basically states that the number of transistors per chip double every 18 to 24 months at a constant cost. So this is rather not a law, it's an observation that Gordon Moore made around 1965. And we have used this to predict the compute performance increase year on year that's coming out from our silicon. And typically what we've seen is that the compute performance doubles every 18 to 24 months, mostly coming from the shrinkage in the geometry, the scaling down of the nodes, the increasing of frequency and such things. But that has to happen at a constant cost rate. So that's just keep that in mind. The constant cost is an important factor here. The next one is Dennard scaling. Now, Dennard scaling basically states that as transistors get smaller, their power density stays constant. So basically, as you scale down, the voltage and currents can be scaled down as well. In other words, if the transistor density doubles and the power consumption stays the same, with twice the number of transistors as we move from one node to another node. So that's the other law that kind of govern compute for a number of years for us now. And the third one here is Amdahl's law. So Amdahl's law deals with parallelism in computer architecture and gives us a mathematical formula for boost of any algorithm, application, or system if they are run in parallel. Typically, every algorithm, system, or application has got two parts. It's got sequential parts and it's got parallel parts. And there is a limit to what you can do when you put the same thing in parallel on heterogeneous elements. So what's been happening in the industry for so long? If you look at 35-year trends of microprocessor data, and now we have got trends which are going up to 42, 45 years. What we see that Moore's law is clearly slowing down. The lower nodes are becoming very, very expensive. And when I spoke about constant cost, the cost is no longer constant because moving from 16 nanometer to 7 nanometer to 5 and now 3 nanometers, it's becoming very, very expensive. So clearly that scale side of things as we move from one node to another has slowed down considerably in the last couple of years. In the same way, Dennard scaling actually pretty much came to an end in the mid 2000, actually around 2004, 2005 time scale. And that's mainly because when the Dennard scaling law was formed, they didn't factor in leakage currents and threshold voltages. And now we're seeing as we scale down, there are limits to Dennard scaling. And today 4 gigahertz is pretty much the maximum maximum achievable clock speed that we can get in a microprocessor or a computer. So that's kind of a limit that we've had. And finally, Amdahl's law. Again, we all know if you put 2, 4, or 8 CPUs to a task, they don't really increase the performance of an algorithm or an application 2x, 4x, or 8x. So there's clearly a lot of challenges in parallelizing these algorithms on a single homogeneous architecture. The other thing to note here is we also see issues coming around memory bottlenecks and data flow bottlenecks. So that's the the state of the world at the moment. But what's happening on the requirement side? And I've picked up one example, which is compute needs for AI training systems. And up to the last decade, up to 2010, we were seeing that the compute needs by the industry for this particular use case was in line with what we were able to get from going down nodes or increasing clock frequencies and things like that. But over the last decade, we've seen a massive increase in the need for compute from these systems. Typically, they are going at 10x per year. And clearly the industry, the 3 traditional laws that we've looked at are not able to fulfill or furnish these requirements now anymore. So what is the solution? Where do we go from there? And I think the easiest way to look at is look at the nature. I believe the most well-formed, perfect, efficient compute machine on this planet is the human brain. And if you look at the human brain, you will see that human brain is actually a heterogeneous architecture. By heterogeneous, I mean the part of the human brain which is designed or connected to do vision has got a different architecture from the part of the human brain which is designed to perceive audio or some of the other functions. So the human brain itself, it's a complex compute engine, but it's formed of various heterogeneous elements in itself. So coming to how we define heterogeneous compute. So within imagination, or the way we look at heterogeneous compute, we define heterogeneous compute as the execution of tasks on set of discrete computer architectures, enabling specific operations to be computed in the most efficient manner. Now, I think this is important. The efficient manner is a very important part, because of course you can run things on different compute elements, but they need to run the most efficiently, as per the need of that application. Here, I've also given an example of a heterogeneous compute, a use case. This is a face recognition-based access control. So this is what is happening today. You have image which is captured by a lens or a camera, which is then goes through some level of image processing. Things like dewarping, noise reduction, demosaicing happen either in a GPU or in specialist function units like the ISP. But there is a GPU plus CPU heterogeneous work management that happens in image processing. Then you move on to feature extraction and matching. It's where the CPU works alongside traditionally a neural network accelerator to run convolutional neural networks, do algorithms like HOG and SVM, and then ultimately the CPU would actually either grant access or not grant access. So this is what is happening in the heterogeneous systems today. But what about, we here at Imagination, we're thinking about what happens about these heterogeneous systems of tomorrow. And we look at three key ingredients of these heterogeneous systems. The first and foremost is the compute element itself. And there are different compute elements that can come in a system. They can be, general purpose CPUs, which are good at sequential management of workloads. There are GPUs, which are more suited for parallel workloads, floating point workloads. Then there are neural network accelerators, which are good for neural networks and CNNs type of applications. The second important thing in this is the efficient data flow across these compute elements. And the third, of course, is the software tool and frameworks. So all of these three elements are required to function hand in hand appropriately to give you the right heterogeneous compute system. So we at Imagination, we are working at resolving data bottlenecks as these systems scale, because scalability is another interesting angle that we need to look at. We are working to optimize memory and cache architectures, security and safety particularly in most of our applications, and security from say automotive type of applications. So we are working on producing solutions which have got end-to-end security. Highest possible performance at the lowest energy envelope. So there's another trivia that I can share with you guys. It's predicted by 2030, around 21% or 22% of the worldwide energy consumption will go into things like data center, networking devices, and things like consumer electronics. Now, we cannot allow the energy to go in the same way as it's being, being used today. So we need efficient solutions for the future. And of course, all of this has to be developed, deployed, and programmable and updatable in a easy software model where the frameworks, tools all work efficiently. So at Imagination, we have got a rich portfolio of these IPs, which we are trying to bring together. The GPUs, we have a market-leading GPU, embedded GPU offering, which goes into automotive markets, mobile markets. We have a very strong neural network offering and a connectivity offering around Ethernet solutions. And very recently, we started to work on RISC-V based CPUs, and we are bringing those to the market. So why RISC-V based CPUs? I think RISC-V based CPUs are actually democratizing and accelerating the compute today. It's a neutral body, a non-profit body, which has got very limited geopolitical challenges. Our geopolitical environments are quite unstable these days. It's a growing ecosystem, a very strong ecosystem of 1,000 plus members already. It's a modern scalable architecture. It's built out of 30 years of research into RISC architectures. So it's not a brand new architecture. It's built upon something coming from 30 years of research. And it's got a lot of support, both in academics, now full Linux support, and tool support, including GCC and LLVM. So it's a very unique product that is coming to the market, or unique architecture that is coming to the market that will enable heterogeneous compute in the future. So we at Imagination, we've been working on these complex IPs for a number of years, almost 3 decades now. So we're bringing all of that knowledge together to deliver the next generation heterogeneous compute solutions. And of course, we bring them with the right level of protection for our customers, with sort of right level of patent coverage and support and innovation for next generation applications. Quickly, I think I will touch upon the first product that we are bringing in this sort of story of heterogeneous compute, which is a dual issue in order CPU. it's an extensible architecture. RISC-V itself is an extensible architecture, and we are bringing all that good features of RISC-V extensions into our CPUs. So I'll not go through the details, but it's a fairly complex but a flexible 32-bit 11-stage pipeline CPU that we're bringing to the market. Initially for embedded applications, but moving towards Linux-based systems as well. Sorry. So of course, we are also bringing a full software SDK support, as well as a Visual Studio Code-based IDE with this CPU. Quickly looking at the direction of travel for us. So as I said, we're bringing the 32-bit RISC-V processors right now, followed by application processors, which will enable Linux-based applications. Then followed by multi-core systems. Then we are moving towards high-performance out-of-order CPUs, 64-bit architecture CPUs, and then we are working towards next-generation heterogeneous compute platforms. So that's happening in our research today. And touching upon all the points that I mentioned before, end-to-end security, data bottlenecks getting resolved, and a homogeneous sort of software environment for all of these elements. And this is, I think this is my last slide, where it's just showcasing what kind of a heterogeneous system we are working towards. So on the left-hand side, you have a hardware conceptual block diagram of various compute elements sitting in a coherent or a network fashion with different CPUs, some high-end, high-performance CPUs, some more in-order, high-efficiency CPUs, sitting alongside neural network accelerators, GPUs, which are good at performing parallel compute, and some custom hardware accelerators as well. So that's on your left-hand side. On the right-hand side, the story is not just about the hardware. It's about how do you deploy these things in actual applications. So we're bringing together a complete compute stack that can enable developers to run their applications on the right hardware element that's needed. So if it's a parallel application, floating point, it can go to GPU, sequential one on a CPU, and of course, a TensorFlow based or a CNN can run more efficiently on an NNA. So I think that's my last slide, and that's from me. So any questions?
Thank you, Shreyas, for a really important topic of new era of compute and the role imagination is playing in defining it. So you talked about CPU, GPU, and NNA. What other compute elements are emerging? We have heard about DSP before. Do you see any new emerging programmable or fixed components that are becoming important?
So what's happening really around RISC-V is an extensible architecture. So what if you have certain compute needs, basically they are getting furnished through newer instructions getting added on the CPU side. But of course, there will still be a lot of custom compute elements. So if you wanted to do certain kind of mathematical algorithm that is, very heavy in your ultimate application, you would rather do it on a custom hardware element, and that will come along as extensions either to RISC-V or stay within sort of the current networking infrastructure that we have.
Sure. Thank you, Shreyas. And I just want to talk to you about your tools. I mean, how does a user or a programmer who's trying to use a heterogeneous environment, how do they profile and partition the code into various compute elements?
I think that is kind of, I would say, the holy grail of heterogeneous compute. If we can do it automatically, that would be the ultimate solution. It's still manual today, whereby the application developer understands where best he needs to run the application. But we are working on ideas whereby it will be all done by the overall compiler, and the compiler would exactly know which part of the algorithm needs to run where. So there is a profiling step that has to happen before that.
Thank you, Shreyas. Let me just check if there are any more questions. Okay, that's all, Shreyas. Thank you so much for attending from UK and giving a really good presentation.
Thank you very much.
Bye-bye. Thank you. Hello, everyone. We'll move on to our second speaker today. Our second speaker is from Synopsys, Desai. Harsh is Senior Manager of R&D in Synopsys, and he has held various positions in Synopsys for the last 15 years for product development and various other development opportunities as well as program management. Harsh is joining us today for giving a talk on data analytics for high volume semiconductor using AI and ML techniques. So over to Harsh.
Hello everyone, this is Harsh Desai. I'm from Synopsys, and today I'm going to talk about importance of AI/ML in chip manufacturing. For today's agenda, I have a couple of points. We'll talk about data landscape in manufacturing, then we'll talk about traditional semiconductor manufacturing process flow, benefits of using AI/ML in manufacturing, and conclusion. So without any further delay, let's just dive into data landscape in manufacturing. So in this, imagine in 60 seconds what's happening around us. People are using social media, messages are being sent, emails are being sent, photos are being shared, streaming is being done. So this generates a lot of data, and a lot of data in terms of zettabytes. And the estimate says that by the year 2025, 163 zettabytes of data will be created. Now, to process this data in a timely manner and give user a feedback, will require a faster CPUs and GPUs and larger storage every 4 months. And this data growth will continue to grow. Now, what this impacts and how it impacts on the chip manufacturing. So the fabs which are producing the wafers and chips, if you consider the database size in earlier years, in the 1990s or so, the database size were 500 GBs or something per year. Now we are talking about 10 terabytes a year. Number of wafers which are processed has increased to 1 million per year. Dies have increased also. Defects, if you see, which has help of sophisticated tools, the number of defects which are found, they are also very large. The image size is also keeps on continuing to increase. An important aspect of is a process steps. Now, process steps have also increased to more than 1200. Now, this talks about the the volume of data which fabs have to process. Now, with this volume of data, the traditional way of semiconductor manufacturing process that used to do what the data sources were equipment. Raw files were being processed and it was stored on some database. Some of the things which were, they are normalized and correlated and all. And then the root cause analysis was primarily the responsibility of operators or the engineers. They have to spend a lot of time, and with the highest volume of data, this kind of volume of data, you're talking about, the duration to be going to days or months even for some of the instances. Now, this caused basically the yield phases to grow to at least 2 years, because the process RAM used to take around 6 to 9 months. Product RAM is taking around 3 to 6 months, and production RAM is going to be 6 to 9 months. So, with this huge volume of data being processed and processed manually in most of the cases, the time to market is getting very, very long, which is opposed to what we talked about, that with the explosion of data and the need of processing data, it keeps on increasing. And so the manufacturers or the customers cannot wait long for having this production delays, right? So what's the solution? Solution here is that implementing the automated processes of AI and ML, which will help or reduce the time to market for customers, because some of the tasks or some of the applications which can automate many of the tasks and reduce the overall cycle. Now, why AI ML is important? First, it's a low cost uh, as compared to the devices and all. Then it's efficient. It has improved yields and results for the customers and fabs. It can run in parallel. You don't have to wait for sequential execution. Doesn't have any bottleneck. It's very high speed, and most importantly, it is node agnostic. When I say node agnostic, means that even with the lower nodes, you don't have to rewrite the whole algorithm. The algorithm itself is you can run it on 7 nanometer, 5 nanometer, or uh, 10 or whatever. You can do that. That's how it works. So in the fab, there are typical applications which are used in manufacturing. First is wafer map classification, wafer map pattern classification. Now, this application basically helps users to figure out if a pattern on wafer A was observed previously on any of the wafers, and then what was the yield for that. Right now, this analysis is done manually and time consuming. Now imagine if incoming wafer loaded into the database has the AI application will predict and will go back to database and search that which all wafers have similar patterns. The other application is automatic defect classification. This basically is the classification of images uh, based on certain structures and signatures on wafers. Right now, the classification process is very time consuming. To give you a perspective, the large foundries, they are generating millions of defects in a week's time. Now imagine if operators have to sit and manually look at each of the images and then classify to figure out the killer classification, it's going to be very time consuming. So there, the AI algorithms can help in detecting the and classifying images. Then we have root cause analysis. Then we have tool matching. Now here, the purpose of tool matching is basically that if tool A has seen certain parameters or certain readings which are maybe considered abnormal or something, then the algorithm will try to figure out in the past which other tool had similar kind of anomaly and what was the yield at that point of time, so that you can predict and do a preventive maintenance of the tools. Then fault detection and classification. This also is another important AI application in the fabs, where you are basically identifying the parameters or sensors on the equipment which are causing a problem, and then you are classifying the faults, and first you are detecting and then classifying the faults, then detecting outliers at short wave, then advanced process control. So the applications of will actually go a long way to reduce manual work and improve efficiency for the fabs. Now, what's the impact of this? And this is a typical, representative impact of yield. We talked about process ramp, product ramp, and production ramp, right? In earlier slides. Now, if we apply AI and ML applications into the manufacturing process flow, then the impact of yield, you can see the green line versus the red line. you have a higher yield at a lower time. So the cycle is very reduced. And that's where the beauty of and importance of AI comes into, for manufacturing comes into picture. And these are the examples, some of the examples how AI applications are going to reduce the overall time. So root cause identification, we have taken example of 3 customers that it used to take do a root cause identification using traditional analysis. It used to take 7 days. Now with the help of AI/ML and ready results, we'll be able to achieve that in 4 hours. Similarly, from 3 weeks down to 3 hours, and sometimes the users could not find the root cause even in weeks time. There, the applications of AI can be applied, and the results could be found within 5 hours. So basically, higher yields with application of AI, and with higher yields, you'll always have the increased profits. Now, with that, I come to a conclusion that the application of AI/ML will dramatically accelerate the semiconductor industry over few years. And to compete, semiconductor companies need to be more rapid and agile than ever. The advent of AI and big data will only strengthen their performance and profitability, as AI can allow semiconductor companies to capture more value from the technology stack. With that, we'll talk about question answers now. Thank you.
Thank you, Harsh, for a really wonderful talk on using AI and ML in manufacturing process. So one question, what kind of networks, AI, ML network topologies do you use in the manufacturing, yield improvement and process improvement?
There are multiple network topologies. One of the topologies so practically, to answer your question, it's not a one-liner answer I can give you. It will depend upon the nature of problem we are addressing. At this point of time, we have addressed the problem of, let's say, an image classification, for an example. There we are trying to use, CNN to get the best result. But if you have the statistical data, it may not be possible to use that, right? So it depends upon the problem statement what we are trying to address. And then it can be best suited, or the best suited topologies can be used.
Okay, thank you, Harsh. There is one question from Samira Bhardwaj. So first of all, very informative presentation. Thank you for that. Is tool matching typically done node/tool pairwise with respect to a reference node in practice?
So in practice, the tool matching is done at a process level, right? So the process will be at a node specific. Let's say if I am processing a wafer of 7 nanometers, the process will remain same, and the tool which is processing those wafers will also be the same. So that's where the tool matching will done. So if I have to give a simple answer to that question, it is more of a the reference node level at which the equipment is being used.
Okay, thank you. There is one more question from Shashank Agashe. During development, data may be insufficient or drift till it reaches production. How is this typically handled?
Oh, that's a great question. And thanks, Samira, also for that. It was a great question also. Just, the tool matching problem that we had struggled for a lot of time, and then ultimately we have mastered that art of tool matching, and figuring out which exact process steps or which exact tools are causing problem. And for Shashank also, that's a great question. So whenever you talk about AI or ML applications, right, the reference data is the most important part. if you don't have enough data for you to develop a model, you will not get accurate results. So the thumb rule of AI/ML is basically garbage in, garbage out, right? So if you give an insufficient data, you are going to get insufficient result, right? If you are going to get incompetent data, you are going to get incompetent result. For training the AI and ML models, you have to get the data, as much data as possible for your model to train upon. Now, there are other aspects also for unsupervised learning and the manufacturing process, which the work is already in progress, where even if you don't have enough data, you can actually apply or simulate data based on the previous experiences what you have. There is a concept called digital twin, which is in works right now. What happens is basically you are trying to mimic the whole manufacturing process in an artificial way, right? So based on the previous data patterns, you have the simulators embrace the data, which ultimately will be fed to your AI/ML model and make your model more accurate and easy to train. So that's what my answer would be, that if you have insufficient data or a drift in data, you might want to try and look at your previous data and then try to simulate the data to optimize your AI/ML model.
Okay.
I hope I answered both the questions.
Sure. Thank you, Harsh. Thank you for your presentation and question and answer. Appreciate it. Okay. With this, we'll move on to our final speaker for today's session. Our final speaker today is Karthik Ramasubramanian from Texas Instruments. Karthik is currently System Manager and Radar System Architect at Texas Instruments. He has 20 years of experience in system engineering for wireless LAN, GPS, and automotive radar systems. He is currently Distinguished Member of Technical Staff at Texas Instruments and has numerous patents in GPS and radar area. So with that, I'd like to welcome Karthik to give his presentation.
The title of my talk is Role of Automotive Radar and Emerging Trends Towards the Future of Autonomous Driving. Here's a brief outline of my talk. I'll start with an introduction to FMCW radar, which is the most popular radar modulation scheme used in the automotive industry today. I'll cover some of the industry trends in this space. Then I'll talk about two key innovations in the form of highly integrated CMOS-based radar on chip, as well as a high angular resolution imaging radar that TI has developed. And then I will cover some of the emerging applications, such as in-cabin applications, which is gaining a lot of prominence in recent years. So here is a brief introduction to automotive radar. The use of radar in automotive applications has evolved rapidly in the last 2 decades. So if you see the picture on the right-hand side, it started maybe 2 decades back with just a single front-facing radar, long-range radar, which was used for adaptive cruise control type applications. Since then, the applications have evolved significantly, and now there are multiple sensors around the car serving a wide variety of applications, both safety as well as new applications like what I have listed here. There is emergency braking and blind spot detect, lane change assist, cross traffic alert, and also new applications like replacing ultrasonic sensors with radar for park assist, as well as 360-degree surround view, and also in-cabin applications for features like child presence detect. And the automotive radar market is expected to grow quite significantly over the next 5 to 10 years, as it's seen from many industry reports. Here is an overview of FMCW radar. FMCW stands for Frequency Modulated Continuous Wave. there are many different modulation schemes, all the way from pulsed radar to FSK, UWB, and so on. But FMCW radar is the most popular in automotive applications. And if you see the picture on the right-hand side, in FMCW radar, the transmit signal is basically a linearly varying frequency. So the transmit signal starts with a certain start frequency and changes linearly in frequency, and it's called a chirp waveform, which is shown in the red colored waveform picture in the picture on the right. And the major benefit of this modulation scheme is that you can sweep a wide RF bandwidth. You can sweep 1 gigahertz, 2 gigahertz, 4 gigahertz bandwidth, which is very important to get good range resolution. But you can still keep the ADC and IF bandwidth very small, and that's a big advantage. The other big advantage of the scheme is that it requires lower peak power, unlike pulsed radar, for example. And radars, the output of radar is it gives you the range of the object, it gives you the speed, relative speed, as well as the angle of arrival. So these are the output that you get from the radar. Now we'll talk about some of the industry trends in this space. First of all, many of the short-range radars, especially the corner radars in the industry, were based on 24 gigahertz, but they are in the last several years moving towards 77 gigahertz multi-mode. And what this means in terms of the sensor requirement is 76 to 81 gigahertz support with flexible chirp waveforms, so that the multi-mode use cases can be adequately solved. In terms of the waveform, I didn't talk much about it, but there used to be a legacy slow FMCW waveform, but that is being replaced by fast FMCW modulation, which uses this multidimensional FFT to get the range and velocity unambiguously. And that requires wide IF bandwidth and high sampling rate. A key trend in the industry is the movement from discrete solutions to highly integrated solutions, and this means fully integrated CMOS-based radar-on-chip devices where the millimeter wave RF, the 77 gigahertz RF, and the DSP and all the processing is integrated into a single device. Newer applications and high resolution means wide sweep bandwidth. Like I mentioned, 5 gigahertz, 4 gigahertz bandwidth support in the 76 to 81 band, and very precise chirp synthesis. Safety functions, it's no longer the radar is no longer used for just driver assistance comfort functions, but also critical safety functions, including emergency braking and so on. And this requires better functional safety features in the device, monitoring mechanisms to make sure that in case there is a failure, it is immediately detected and reported. High angular resolution and imaging, I'll talk more in detail about this. This means you need more and more transmit-receive channels and cascading of multiple devices. In terms of more recent trends, there is an increasing interest in using radar for in-cabin applications, which I'll talk about also in a later slide. And this is happening in the 60 gigahertz ISM band. Small form factor is another key trend that is, and the use of radar for obstacle detection. For example, opening the door, you open the door and you want to detect any obstacles, which requires a small form factor so that the radar sensor can be put in small, places like door handles. This requires the antenna to be integrated with the package, and I'll talk more about that as well. Cybersecurity is a big requirement for all automotive sensors and all the ECUs in the vehicle. And there are standards and evolution of cybersecurity requirements that need to be factored in the device development. Another new trend is the use of satellite topology, where the radar sensors do not do all of this processing in the edge, but they send out raw data over a higher speed interface like a gigabit Ethernet or SerDes to a central processing unit, and the central processing unit does all the fusion of raw information from the various sensors. So what are the main challenges and opportunities here? The industry is moving towards the vision of autonomous driving. Multiple sensor technologies are available and are being used. There is ultrasonics, radar, camera, LiDAR, and so on. Now, when we compare radar with other technologies like camera or LiDAR, the main advantages that radar brings in are listed here. One key advantage is that the radar works even if there is smoke, fog, or dust. And typically, the vision-based technologies have limitations in such situations, including, when there is dazzling bright light, or in cases where there is no ambient lighting. Also, radars can operate behind plastic enclosures compared to camera, where there are privacy concerns. Operation behind plastic enclosures. This is more relevant for other applications, not necessarily ADAS or autonomous driver assistance, but for other applications, there is an advantage that radar brings in compared to camera technology. In terms of key challenges and opportunities, I'll talk about the angular resolution, which is a key limitation of conventional automotive radar, and how there is an increasing need for more and more channels, transmit and receive channels, to get much better angular resolution in radars. Interference across radars is another key challenge. With more and more radars getting deployed, how can interference across radars be solved? And this requires advanced algorithms and system level solutions. Another area of interest is object classification. When you use an imaging radar and you get the point cloud, how can we classify the object? And that involves the adoption of machine learning techniques to address that. Now, this talks about highly integrated CMOS based radar on chip. As we talked about earlier, instead of discrete solutions, like you have a front end, which is typically called the MMIC, the RF portion, and you have a separate device doing the digital processing. Compared to that, a highly integrated solution is more efficient in terms of form factor, cost, and so on. So in TI, we have been developing highly integrated CMOS-based radar on chip. This is our second generation of it. And this device includes 4 transmitters, 4 receivers in the 77 gigahertz band, all of the RF analog circuitry, and the entire digital processing with a DSP and a Cortex R5 lockstep with all the safety features, as well as interfaces, including automotive interfaces like CAN-FD and Ethernet. So all of these are integrated into a single device, and that is the AWR2944, which can be used as a single chip premium corner radar solution. And it comes with all the functional safety as well as cybersecurity features that are required for such a application. Now, I talked about angular resolution and the need for imaging radar. So here's some more details behind it. So what is the angular resolution problem? Radars, even though they can detect the range and velocity with high precision, they have poor ability to resolve objects at the exact same range and velocity. So what it means is that if you see this picture, if this represents the field of view, objects at different distances can be resolved very nicely by the radar. And also objects having different velocities can be resolved. But if you see at the same distance, if there are multiple objects, each object, you can see how it is smeared in angle. And that is a classic problem because of the limited number of transmit and receive channels. And this can be a key disadvantage in many situations, specifically, identifying overhead bridges and maybe signposts, drive under, I mean, overhead bridges, you can drive under it, but if you do not have sufficient angular resolution, then it becomes difficult to discern that scenario. Drive over situations, maybe you have a small object on the road that you should just drive over, and that is something that requires high angular resolution. Similarly, if you look at a park assist scenario, detecting a curb requires high angular resolution. So these are some examples why there is a need for what we call as imaging radar. Now, what does imaging radar mean? It simply means a significantly higher number of transmit and receive channels to get much higher angular resolution. And one way to achieve this is by cascading devices. For example, if you take two devices which have 3 transmit and 4 receive. I'm showing an example here on the right hand side, which is the TI-2243 device, which has 3 transmit and 4 receive. And if you cascade 2 of them, then it can give 4 times higher angular resolution. Now, when this is done, it's important to make sure that the local oscillator, the phase is synchronized across these devices. And so the master device and the slave device must be phase synchronized for beamforming to get the high angular resolution. And this is achieved in the 2243 device through routing a 20 gigahertz version of the LO or local oscillator from the master to slave. And also many other factors like ADC sampling synchronization have to be factored in to achieve the performance that is required for high angular resolution. This is an EVM that shows how this imaging radar cascading looks like for 4-chip cascading. And so here you see 4 2243 devices. They all function in a synchronized manner, and it allows 12 transmit and 16 receivers to operate simultaneously, giving 192 virtual channels. And this gives high angular resolution and very high range that is required for the future high resolution radar. And this kind of a solution is already shipping in the industry today with the 2243 device. And here you can see how in this case there are multiple objects or people and cars and bicycles here, and the radar can detect all of them and separate them out nicely as it is shown here. And it has not just the azimuth angle, it can also sense the elevation angle and show the height, which is very useful for classification applications. I'll now talk about some of the emerging applications. I mentioned in-cabin applications as another new trend that has picked up significant traction in the industry in the last couple of years. And here, the purpose of the radar is to do child presence detection as an example at the lower end. This is an important Euro NCAP 2023 feature where if there is an unattended child that is left behind on a hot day, that the radar can detect the presence of a child and raise an alarm. And this is one new application. And here 60 gigahertz radar is being used to solve this problem. And there are other applications as well, a seatbelt reminder or an occupant monitoring to figure out, the occupancy inside the vehicle, the different seats, as well as applications like intruder alert, where the radar can monitor if there is an intruder near the vehicle. Another key trend that I want to highlight is antenna on package, which has many benefits. At 77 gigahertz, you integrate the antennas on the package instead of having antennas on the PCB. And this eliminates the need for expensive PCB material. It brings about significant form factor benefits, which is very important for some of the new applications. And it also makes millimeter wave RF easy for customers because they don't have to worry about the routing the 77 gigahertz or 60 gigahertz RF and design a PCB to manage all of that. And here I'm showing the 1843 and 6843 devices, which are 77 and 60 gigahertz single chip devices with AOP, which is antenna on package. And you can see that the device has the 3 transmitters and 4 receivers on antennas on the package itself. So in summary, automotive radar technology has evolved significantly over the last 2 decades, starting with premium vehicles where the technology was adopted initially to now mid and entry-level vehicles as well. And there are multiple sensors in each vehicle, and the applications cover all the way from comfort functions to safety applications and more new applications emerging. And highly integrated CMOS-based radar-on-chip devices are further accelerating the adoption. And imaging radar for high resolution enables more autonomous driving features because of the ability to separate out objects in angle, which conventional radar isn't able to do. And new applications like in-cabin applications are gaining significant traction. So that concludes my talk. I'll be happy to take any questions.
Thank you, Karthik, for a really nice presentation on automotive radar and some of its applications. So I have a question in terms of the stringent requirements between the in-cabin and outside the car. Where do you see more tighter requirements for both safety as well as for some of the performance parameters?
So certainly the exterior radar meant for driving assistance, autonomous driving type applications, that has high requirements on performance, safety, and so on. In cabin, because of the short distance involved, it does not have exactly the same kind of performance requirements. Maybe it can be considered a slightly lower performance requirement. But in both cases, the performance requirements are constantly going up. For exterior radar, I talked about imaging radar, where you need a lot more channels. You want to discern a bridge and a Coke can and the parking curb and so on. So the number of channels, the performance requirements, the safety requirements is all going up. In-cabin is slightly lower right now, but even in cabin, the performance requirements are starting to go up because you want to be able to figure out. Even within the cabin, there are applications like seatbelt reminder where you need to be able to separate out, who is sitting in which seat and use that information. So there also the angular resolution requirement and performance requirements are going up. But generally, the exterior one is much higher in terms of overall performance requirement.
Okay, thank you, Karthik. Yeah, one more question. I saw in your block diagram, you're integrating both complex analog as well as the digital functionality, for example, DSP and ARM processors. So how do you decide what kind of process technology to use for integrating both highly complex analog as well as digital?
Okay, so the current generation of devices, we are in 45 nanometers, and certainly, the RF performance, because of the high frequencies, 77 gigahertz and 60 gigahertz involved, there has been a lot of effort put in to optimize the RF at millimeter wave at this particular technology node. But we are also looking at next process technology nodes to further, get the benefits, especially on the digital side, with the, with lower technology nodes. So this is something that, depending on the maturity of the process and especially the RF circuits at the different nodes, we are looking at further optimized form factor with lower technology nodes.
Okay, thank you, Karthik. Once again, Karthik, thank you so much for your presentation and question and answers.